Okay. Okay. A while back, before taking a break for a test, I had started chapter 3 on determinants. So now this week I'm going to continue and actually finish that chapter. It's a short chapter on computing determinants in various ways, and also applications of determinants. Speaking of a test, so over the weekend I reviewed all of them for partial credit. I know the scores were already pretty high, but now they're higher still. I believe the average turned out to be around a 93. I think a median was about a 97. So nice job, everyone. And so we'll see if we can duplicate that for the final. Excuse me. All right. So first I'm going to quickly review certain aspects of computing determinants and certain properties that they have that are helpful towards computing determinants. So first, if we have a matrix that is triangular in any way, so lower triangular or upper triangular. So lower triangular means that all the entries that are above the main diagonal, that should be main diagonal, are 0. Or if it's upper triangular, then all the entries below the main diagonal are equal to 0. And we do have an example of that in one of our problems. Like, okay, here, this is an example of a upper triangular matrix. So if you have any kind of triangularity, then the determinant is really easy to compute in that case. That all you have to do is take the product of the diagonal entries. So that's how you handle a triangular matrix of any kind. So what that means is to compute a determinant, you can start by performing row operations on the matrix to get it to echelon form, which is for a square matrix like we're talking about here, that would be an upper triangular matrix. So in that case, if you perform row operations and then get it to echelon form and then take a product of all the diagonal entries, that's actually a lot more efficient way of obtaining the determinant than the way I've shown you by using a cofactor expansion along a row or column. So in fact, I'll make a comment about that. Okay. So if a matrix is n by n, cofactor expansion, the number of operations, arithmetic operations, is on the order of n factorial. And the way you can see that is when you're doing cofactor expansion, you're having to compute for n by n matrix, you have to compute a determinant of n matrices of size n minus 1 by n minus 1. So what you're doing is you're taking the amount of work to compute the determinant of a matrix of one row and column less, and then you have to multiply that by n. So every time you go up in dimension, so from n minus 1 to n plus 1, etc., you're multiplying the amount of work by that dimension. Well, that's a factorial. So this is horribly expensive. On the other hand, reducing a matrix to echelon form and then multiplying the diagonal entries, that requires order n cubed operations. So a whole lot better because n factorial grows a whole lot more than n cubed. Now, that doesn't really affect things for kind of problems that we're doing in this class, just because we're always dealing with very small matrices, 3x3, 4x4, etc. But once the matrices start to get a little bigger, then the amount of work to compute a determinant by cofactor expansion grows very rapidly with the size, but not so much when we're doing row operations. So if you're trying to get the determinant by reducing a matrix to echelon form and multiplying the diagonal entries, then it's important to know, as you do row operations, does that affect the determinant? So for the most important row operation, for getting echelon form, adding a multiple of one row to another, no, that does not change the determinant at all. The other elementary row operations do change the determinant. So if you multiply a row by some number, then that determinant is multiplied by that same number. And also, if you swap rows at any time when reducing to echelon form, that will change the sign of the determinant. So as long as you keep track of those things during the reduction to row echelon to echelon form, then you'll be able to get the proper determinant. That's something that I'll show you in some of the problems that are coming up today. All right, so all this deals with how row operations affect the determinant when they do. Then we also have several formulas that can help computing certain determinants. For example, if you have a determinant of a product, then you can take the determinant of the two matrices being multiplied individually and then just multiply them. Also, if you multiply the whole matrix by a scalar, then that multiplies the determinant not by that scalar. That only happens if you multiply a row by that scalar. But if A is n by n, you got to multiply by c to the n. I've mentioned before, this is a common mistake that students make when computing determinants. They think, oh, determinant of 2a, you just take determinant a multiplied by 2. No, it's multiplied by 2 to the n. But transpose, if you take a determinant of a, it's the same as the determinant of taking a determinant of a transpose. I've previously defined a determinant in terms of expanding across a row or a column. So it makes sense that since you compute a determinant either way, that just changing a sense of rows and columns will not affect things. And sure enough, it doesn't. This property here, actually these last two, are consequences of this one, that the determinant of a to a power, you can just take the determinant of a and raise that to that same power. So you can basically move the exponent out. And finally, if a is invertible, so a is invertible if and only if its determinant is non-zero. So in that case, to take the determinant of the inverse, you just take 1 over the determinant of the original. That makes sense because a times a inverse is identity. So the determinant of a times the determinant of a inverse ought to equal determinant of identity, which is 1. Okay. Now we'll use some of these properties, I mean, actually I think all of them, in working through these problems. So the first few are about taking a matrix like this and reducing it to echelon form and getting the determinant that way, by getting it to upper triangular form and then multiplying the diagonal entries. Now, this notation where I have a vertical bars, because customarily I have square brackets, but when we have a vertical bars, that's referring to determinant. So what I have here is not just this matrix, but it's the determinant of this matrix. So if I do the customary row operations, for instance, I eliminate this entry by adding the first two rows together, that will not change the determinant. So in other words, the determinant of this matrix that's simpler is equal to the determinant of the original. So then I keep going. So I take this row and subtract this row times 2 from this row to eliminate this entry. So again, no change in determinant. So already what I could do is I could just take the determinant of this by saying it's equal to 1 times the determinant of this 2 by 2 matrix here, because if I'm doing a cofactor expansion along the first column, these entries are 0, so I don't have to worry about this one. But what I really want to do is keep going to get to echelon form, and I can just multiply the diagonal entries. So to eliminate this entry, so I take twice this row and add it to this row. Again, it won't change the determinant, and I've gotten it to upper triangular form. So the determinant of this matrix is the same as the determinant of the original. So now I can just multiply the diagonal entries, and then I'm done. There's my determinant. Any questions about what happened there? I have a couple more problems just like these, except some different things pop up. So here, same kind of problem. We are reducing to echelon form. So for convenience, what I do is I want a 1 here to eliminate these entries. Divide this row by -3. So when I do that, that means that the determinant of this matrix, so what's between the bars here, is equal to -1/3 times the determinant of the original. Now, I want to explain what I'm doing here is I want the determinant of this matrix. Now, I'm going to get it by taking the determinant of this one, but because I perform this row operation that multiplies the determinant by -1/3, I have to compensate for that out here. So whatever scalar I multiply this row by, I'd take 1 over that and put it out here. And what this is telling me is literally I'm multiplying. So I will get the determinant of this times -3 will give me the determinant of the original. So any row operations I perform that change the determinant, I have to count for that out here. But remember, if you multiply a row by a scalar, put 1 over that scalar out here, that way you're still working on the determinant of the original matrix. And then I can continue the elimination. So I'll subtract 6 times this row from the second row. That kind of operation doesn't change anything. So this -3 is still sticking around from the first row operation, but there's nothing new. Here I'll take 6 times this row and add it to the third row. And then I can perform this elimination. So 15 times this row subtracted from the third row. And now I have upper triangular form. So the determinant of this matrix, I just multiply the diagonal entries. Now it will give me 24. But to get the determinant of the original matrix, I have to take into account that at the beginning, I multiplied a row by -1/3. So basically I have to undo that now and multiply this determinant by -3 to get the determinant of the original matrix. So we get minus 72. There's another one that appears to be a little nastier since it's 4 by 4. So I go through the same kind of elimination process. At least I can skip this entry and then add the first and third rows together to eliminate this element, and then take 3 times this row and subtract it from the last row, and that will take care of the first column. And then I just keep eliminating.
Wait, can you go back up?
Here or further?
Stop. I think I got it.
Okay. All right. So now this column, conveniently, I have a 1 here. So that facilitates eliminating. I need to eliminate these 2 entries below it. So I'll take 5 times this row and subtract it from this next row, and then 10 times this row and add it to the 4th row, and that will eliminate everything below the diagonal in the second column. But then, once that's done, look what I have here. This 0, 0, 0, 25. I want this matrix to be an upper triangular form. And I can't use a third row to eliminate, I can't really do anything to eliminate this entry. Can do is I can just swap the 3rd and 4th rows, the last 2 rows, and then that puts the matrix in upper triangular form. So I'm done with row reduction, but because I performed a row swap, remember that changes the sign of a determinant. And since I want a determinant of the original matrix, I have to put this minus right here. So now what I can do is I can multiply, now it's in echelon form, so upper triangular. I can multiply all these diagonal entries, which will give me 300. But then I have to remember to negate it because of a row swap I performed earlier. And that will give me the determinant of the original. So I get minus 300. Questions on these problems? Okay, couple applications of determinants. We can use them. Determinant to find if a matrix is invertible. So a matrix, an n by n matrix is invertible if and only if its determinant is non-zero. So that's what we're going to do here. We're going to get its determinant in whatever way. I've just happened to choose performing a cofactor expansion along the first column, just to take advantage of this 0 entry right here. And then, so if I get a non-zero result, then I'll know that the matrix is invertible. So here I carry out that cofactor expansion along the first column. So I have minus 15. So I'm just going to go down this first column. Minus 15 times the determinant of a matrix I get by deleting the first row and column. So that's this 12, 6, minus 20, minus 9. This matrix that you see here will be multiplied by the minus 15. And then I keep going down the column. Remember, you alternate signs. So I'm going to have minus a minus 3 here times the determinant of this 2 by 2 matrix you get by deleting the second row and first column. So that would be the -4, 3, -20, -9. So here I have, this is what cofactor expansion gives me. So now it's just a matter of working out these 2x2 determinants that I get. So I'm using this a 2x2 determinant formula. So multiply the diagonal entries minus the product of the off diagonal entries. And that's what you see here. And then again here. So after grinding out all the arithmetic from here, we get 108. So that tells us that the matrix is invertible, just because it has a non-zero determinant. You may remember some sections back, I presented to you what's called the invertible matrix theorem, which gives a long list of equivalent conditions that are satisfied by an invertible matrix. So, for example, if a matrix is invertible, it's equivalent to its determinant being non-zero. It's also equivalent to its columns, or rows for that matter, being linearly independent. So that's the subject of the next problem. Here you're given 3 vectors from R3. So put together, they would make a square matrix. So if you want to know if they are linearly independent or not, sometimes you can tell just by looking, but most times you can't. So if you form a matrix from with these, by making these vectors its columns, then you can just take the determinant of this matrix, and if it's non-zero, then the vectors are linearly independent. So again, I do cofactor expansion, and I won't take advantage of any zero entries that I have. So in this case, I could use cofactor expansion along the second row. Now, it's important to keep in mind using the right sign, because if I did cofactor expansion along the first row, I'd have plus, minus, plus, in terms of what signs each of these terms have from a cofactor expansion. But when I'm on the second row, that flips to minus, plus, minus. It's because of a formula for determinants using a cofactor expansion that you have this factor of -1 to the I plus j, times a determinant of whatever smaller matrix you have. So that's why I have a minus here and a plus here. So we'll have minus of -7 times the determinant of a matrix you get by deleting row 2 and column 1. So that's from -7, 6, and 6 and -8 that we see here. Then I move to the next entry, plus 8 times the matrix you get by deleting the second row and second column. So we get 6, 6, 5, and -8 here. So then you go ahead and work out those 2x2 determinants as before. And then after you grind through all the arithmetic, we get a determinant of -484. So because the determinant is non-zero, these 3 vectors are linearly independent by the invertible matrix theorem. Right, next, we have using some of these formulas from before to compute determinants more easily. Actually, this notation is kind of ambiguous, but what we're referring to here is determinant of b raised to the 4th power, where we have b here. So So you would not have to compute b to the fourth. It'd be kind of a pain to do matrix multiplication, total of 3 times to, well, I guess you could knock it down to twice, to compute b to the fourth and then take its determinant. Instead, you can compute the determinant of b as given and then raise that to the fourth power. That'd be a whole lot easier. So to get the determinant of b, cofactor expansion again, this time along the first row, again, to take advantage of this 1, 0 entry that we have here. So it's going to be going along the first row. I have plus, minus, plus. So I can have 1 times the determinant of this matrix here, and then nothing here, and then plus 2 times the determinant of this matrix here. So then we go through all the arithmetic to get down to the determinant of b, working out to be minus 2. So then you would just raise that to the fourth power, and then you have a determinant of b to the fourth, which is 16. I wish I'd use parentheses here, because sometimes notation can be ambiguous. It's actually difficult to tell, are they referring to determinant of b to the fourth or determinant of b raised to the fourth power? They happen to be equal, but I think using parentheses would be better. Would be best to make clear what you're referring to. Any questions on this one? All right. One of the properties I gave was the determinant of a product is equal to the product of a determinants. So here we have A and B given here. So all you're doing in this problem is you're just demonstrating that by computing the determinants of A and B individually. So here I'm using a 2x2 determinant formula for both. And then multiplying those and making sure that that agrees with what you would get by actually going to the trouble of computing A and B through matrix multiplication, and then taking the determinant of a result. So for A, we get the determinant of 5, and for B, we have 18. Now, both of these matrices, I didn't have to use the full 2x2 formula because both A and B are lower triangular. Any entries that are above a diagonal are 0. So what I could have done is just multiply the diagonal entries, and sure enough, that would give me the same result. Also, if you have two matrices of the same triangularity, so lower triangular times lower triangular, the result is also lower triangular. So multiplying two matrices of the same triangularity preserves that triangularity. And of course, something you did some time ago, computing the product, where you're going across, like for 1-1 entry here, going across the first row and down the first column to multiply corresponding entries and add them up. And then first row of second column to get the 1-2 entry, which because of a triangularity is going to turn out to be 0. And then similar for the second row to get the entries of the second row of the product. So I just wrote that out, fresh memory as to how matrix multiplication is supposed to work. And then you can take the determinant result. So 15 times 6 minus 0 times 35 is 90, which happens to agree with what we get by multiplying the two determinants that we got. And finally, here we have two matrices A and B. You're told they're 3 by 3, but you're not actually given the entries of A and B just for sizes as well as their determinants. So then that will be enough information to be able to obtain determinants of certain other matrices that are built from A and B. So for example, determinant of a product, as we saw in the previous problem, that's equal to the product of a determinant, so you can just multiply these together. We get that. For the next one, this is where the size, knowing the size is essential. If I have a determinant of 5a, that's equal to 5 cubed because they're 3 by 3. So whatever the dimension is, however many rows and columns, that is what goes here. And then you can multiply that by the determinant of a and get that result. Determinant of a matrix is equal to the determinant of its own transpose. That answers this one very quickly. Also, the determinant of the inverse is 1 over the determinant of the original. And finally, as we saw 2 problems ago, the determinant of a matrix raised to a power is the determinant raised to that power. So we just have minus 9 cubed in this case. All right, so these properties can make determinant computation a whole lot faster in certain cases. Questions about any of these? Okay, I will stop recording at this point, and then we will wrap up this chapter on Wednesday.